So we had to kind of run this on a Mac and on Keynote. So some of the fonts may look really strange. Maybe the pictures won't turn up. Maybe they will. Who knows? Doesn't really matter. This is my... Woo.
If you want to
try not to
press that button there.
Yeah.
The microphone for the room as well.
All right. Can people hear me okay? Excellent. Right. So this is making sure my talk on cybersecurity in the quantum world. Will explain why I can't spell properly in a bit. Your standard, this is kind of me thing. Apparently I'm better known as Liam's dad than John. So there's a few nods there around the audience. So there you go. That's true. I was a civil engineer, got into computing just as a hobby. When the Thames Barrier came to an end about 1981, 82, people would pay me more to train to do my hobby than they would pay me to do my job. And there wasn't a lot of work around, so I didn't. Stopped doing my job, started doing computers, and I've kind of been interested in them all ever since. I would say I am not a quantum physicist, I'm not a quantum engineer, I'm not a cybersecurity expert, and my maths is pretty rusty. So why am I kind of here? Well, quantum is coming. And I was asked, my eldest lad, Liam, is in cybersecurity. I was chatting to him about quantum computers. He said, come along to DC 151, give us a talk about them. People seem to think the talk was, kind of vaguely relevant. And so here I am. So what I would say is, remember the old Richard Feynman quote, if you think you understand quantum mechanics, you don't understand quantum mechanics. This stuff's pretty wild, it's pretty hairy, but you don't need to kind of know it all, just like you don't necessarily need to know how, a chip works to be able to go and program a computer. There was a time probably you did, and we'll come to that as well. But there you go. Now, mostly I just try and spend my time cycling and, do bits of computing that I kind of like. So what is quantum computing? I realise the slides, there's too many words on this. I'm not going to read them all out. I'll post the deck on LinkedIn, on Discord, if I can manage to work out how to use Discord, because I don't know. And the organisers will probably post something on there. So that is actually a picture of the inside of a quantum computer, one of IBM's quantum computers. The sort of filled in bit at the bottom is where the actual chip is. One of the big problems with some forms of quantum computing is they run at pretty much 0 Kelvin. So you've got to get instructions from the outside world that's at room temperature, step down to, micro Kelvin at the bottom of the stack. So that is actually, it gets surrounded in all sorts of shielding for some reason we'll look at as well. And the shielding gets put into other cases and they end up just looking like another computer, which is why I didn't really post a picture of that. It uses quantum mechanics. Quantum mechanics can get kind of weird, and the weirdness is what gets used, or the properties of that weirdness is kind of what gets used to do a different kind of computing. So a quantum computer works fundamentally differently from any other kind of computer. You can't just take a program. You hear lots of things about these, quantum computers run in seconds what takes the right life of the universe to run. Yes, it does, but only if you've got the right algorithm. That you can't just plug in anything, running on a quantum computer, and it works in seconds. They don't really work that way. Certain properties of them lend themselves to certain algorithms that lend themselves to doing things that classical computers can't really do. So we'll get into a little bit of a history of all of this. So about 100 years ago, roughly, people started to realise that Newtonian mechanics didn't really cut it at very, very small sizes at atomic levels. And so some theories of how perhaps things at that scale worked started to emerge. A lot of discussion about it. Einstein himself was pretty skeptical for a long time, eventually came round. And some of the weirdness of that then started to emerge. Things called superposition. The idea that something can be in two states at the same time, which another factor we'll come to. Entanglement, often called spooky magic at a distance, where two subatomic particles, not subatomic particles, two atomic level particles, electrons, photons, can be in conversation with each other over an amazing distance. They used to think that was instantaneous. Somebody's now measured it, and it's way beyond the speed of light entanglement occurs over, but it's not instant. So that's, possibility of a whole bunch of physics coming out of that. Not going to go into any of that. Then later on, they started to think about, well, what are some of the properties of this stuff? And these weirdness, can it change the way we think about computation? And by thinking about the way of sort of starting to get into the thoughts around that, then they started to get into the idea that if you can use it for computation and you can take some advantage of it, could that lead to what is sometimes called quantum advantage, or the fact that we can do something on a quantum computer that in practice you can meaningfully do on what are now called classical computers, or they're called classical computers in the quantum trade, if you like. The most significant of all of these theoretical advances was Shor's algorithm, which is why I can't spell Shor, S-U-R-E. Because Peter Shor, 94, he came up with the idea that you could use these properties of quantum mechanics, the properties of a quantum computer that people like Feynman and Deutsch had postulated in the 1980s. And his brilliance was to be able to use that to break factoring large numbers. That is what Shor's algorithm will do. And literally within days of publishing the algorithm, the NSA had come to visit. It took them 3 or 4 days. Probably, if anyone's worked for the government, it was probably most of that time was spent trying to get their travel expenses paid off, or authorized. But anyway, they did. And as soon as really after that, a lot of money came in. Sadly, to break, conventional cryptography, but that led to other breakthroughs and other thoughts about, what we can do with quantum computers, or what can be done with quantum computers. Through the 90s, they started to do some experiments. Breakthroughs started to get machines, 1 and 2 qubit machines that would work. And then through the sort of 10s, you got to the point where they were built machines with enough qubits in them to actually do some experiments that broke classical, not broke classical computing, but exceeded the abilities of classical computing. And there's lots of arguments about whether they did or they didn't really, but everyone pretty much says, yeah, they did. Okay. And now we're kind of where we are with these. So before we can really understand the quantum computers themselves and some of their implications for cyber, we need to understand a little bit about the theory that goes on, because otherwise what goes on afterwards won't really make a lot of sense, may not make any sense. But anyway, we'll give it a go. So that's the famous kind of Chinese proverb of the wise man who does a favor for the emperor of China. And he says, how do you want me to get repaid? He said, well, put a grain of rice on the first square of a chessboard, then put 2 on the next, then put 4 on the next. So, okay, I'll do that. By the time you get to the 64th square, you've got however many quintillion, zintillion grains of rice on your chessboard. That is exponential growth. It grows really, really fast. If you see the graph at the bottom, you've got 2 to the n, which is the exponential bit compared to n squared. And you can see how these things quickly diverge and they get worse. And it's because of exponential growth that things like RSA and public key cryptography are deemed to be safe. Yeah. And QCs help because they are also exponential. So 101 qubit computer is not 1% more powerful. It's twice as powerful as 100 qubit. They grow phenomenally fast. And that's part of their strength. They don't just run things faster on their own. They run things faster in conjunction with quantum algorithms that take advantage of some of the features that we're going to talk a little bit about. So they've got all these kinds of implications for computational speed, security, communication efficiency, potentially storage, potentially search. In theory, you could store on, at an atomic level, you could store every possible combination of all the books in the world on the amount of storage where one book will be stored, because you can just use these superposition states. It's all a bit weird. It does get a bit weird. So the three main ideas behind quantum or the quantum phenomena are these three. The fact that a qubit, we think and will show and think of these things as things, but actually they're not. They're wave functions, and strictly speaking, they're probabilistic wave functions. We add in on top of that superposition and entanglement. You can use those phenomena to make yourself a quantum computer. I think that's probably one of the diagrams that hasn't come out. Okay, that's good. No worries. I'll explain a picture to the lot of you now. So basically, what should be there is some pictures of waves, and showing some pictures of waves that are aligned, so-called in phase, and their amplitudes of those waves increase. And if you take if you take those waves and move them sort of anti-phase, so that they're out of alignment, out of phase, then they'll cancel each other out. And that's what you can use to that is what is used to create quantum algorithms. You use the phases of the qubits to reinforce the right answer and to disenforce, if you like, whatever the word is, the wrong answer. Yeah? And that's the basis of these algorithms, because in superposition, every possible answer to the problem is in the computer. So it's the question of getting the right answer out of all the possible wrong answers. I hope some more of my diagrams turn up. Oh no, they haven't. Okay. These are just going to be it's going to be interesting. Okay, so superposition. What does superposition mean? Just that. It can multiply multiple states at the same time. It's not that it's either 0 or 1. It's 0 and 1 with some probability at the same time. So every possible answer is in every combination of zeros and ones that is possible can be in your quantum computer at the same time with some probability. And so I'm going to manipulate the probabilities of the right answer versus the probabilities of the wrong answer. What is entanglement? Albert Einstein's spooky magic at a distance. He doubted entanglement for a long time. Even, he doubted the whole of quantum mechanics for a long time. But this is where you get linked qubits can show, it says instant, they're not quite, but for all intents and purposes, they're instant across distance. And it seems pretty much across any distance. You can send, if you entangle two qubits at least, or 2 bits, 2 things, 2 photons, 2 electrons, whatever, and send them off as far as you like and change the state of one, the other one changes instantaneously. And they've done this over at least the scales of up to satellites, I think, actually. They've done it as far away as that now, and it seems to hold. So there you go. There may also be things like quantum teleportation through that. The idea of effectively, well, if you've got this electron here in this state and you've got an electron over there in that state and you change this state and it changes that state, what's the difference from having teleported the electrons from A to B? For all practical purposes, there isn't really any. So, as we say, for our 64-bit computer, every one of those 18 quintillion possible answers to a problem is in there at the same time. If you've got 2048-bit RSA, every possible answer to that, what is the key, is in there. We've got to think about how we get it out. Okay. And at initialization, those probabilities are equal. We'll play around with them with algorithms that make them not so equal. So what we got here? That's a pity that's not a diagram, isn't there? Okay. What should be there is a sphere called the block sphere. And a block sphere has effectively a radius of 1 by kind of definition. And it has some axes. And the top of the sphere represents 0, and the bottom of the sphere represents 1, and every point around the sphere between there is some probability of being 0 or 1. And also, if we go around the sphere, we can rotate around the sphere, and the rotations around the sphere are the equivalent of the phase of a wave. And let's hope. Excellent. Okay, so if we go back to classical computers, you start with a programming language. It kind of compiles to machine code to microcode. Microcode manipulates logic gates. The logic gates combine to perform calculations, and transistors physically represent those logic gates. And that's how a computer works. We don't really think very much about those logic gates anymore when we're sitting there writing our programs. We have to think a little bit about these quantum gates if we're going to write our quantum programs. And yeah, so here are some gates. There would be some gates, and some representations of them. I know I've got it on here, but I'm just seeing what you haven't got. So the most important ones the most important gate is something called a Hadamard gate. It's named after a physicist. The Hadamard gate puts a qubit into this superposition state. You initialize it at 0, you apply a gate, it's now got some probability of being somewhere between 0 and 1. And then you go from there. Yeah. And then these various Pauli gates, as they're often known, represent these rotations around different axes. And here are some. So you get some of these gates which do clearly have the equivalent of classical computing gates. If anybody's ever done any kind of gate logic stuff on there, a NOT gate turns a 0 to a 1, etc. It rotates around the x-axis 180 degrees. So typically, as I say, from these spheres, starts at the top, NOT rotates around the x-axis to the bottom. You've gone from 0 to 1. Hadamard is a 90% rotation around that sphere. Yeah, I probably need I've got a flip chart over there. I might try drawing a sphere in a minute. Now that could take me quite a long time. I won't bother. But now you've got a 50-50. And because these are rotations, you get some really weird gates that have no classical equivalent. R naught, the square root of naught. The first time I read about the square root of naught at the building, I just shut the book and thought, I've got to come back to that when I've got more time to get my head around it. But yeah, once you see them as rotations, these gates start to make sense. Until then, they don't. And you've also got the equivalent of a couple of other gates that you don't really have in classical computing, which are these so-called control gates. So typically what it means is if your one qubit is in this state, you you change the state of another qubit. If it's not, you don't. And you get C0 gates and CC0 gates to Foley gates. A lot of the names of these things were just named after physicists who did, weird stuff, basically, in quantum mechanics. Okay, so in some way we can think about these things as rotations, which they are, and because they're representations in 3 dimensions, you end up with a famous Euler's formula, which is given there, where these rotations are partly described by ordinary maths, if you like. And if anybody remembers the square root of -1 at school, anyone did any of that stuff? Imaginary numbers? And everyone was thinking, what the hell's going on there? Well, suddenly nearly 60 years later, well, not quite 60 years, 50 years later, I've suddenly found a use for them. That's good. Probabilities are described as vectors. That psi thing in the middle there, I'm not sure, I don't know, does that show up? No, it doesn't. Okay. I don't have a pointer. Okay, that line right across the middle there, is some probability represented there. Some probability of 0, some probability of 1. The bit in the middle that's really, really large is the only real thing you need to worry about, actually, which is that sort of intuitively you think the probability of being a 0 and the probability of being a 1 should suddenly kind of add up to 100% or 1 or whatever. And when you first see that it doesn't, you're thinking, no, beam me up, Scotty. The reason it doesn't is because you have to go into the maths to work out why, but you get into the fact that the squares of the probabilities of those things are what you need to add. You square them and then they add up to 1. That's about the only real maths you really, really need to understand. But there's a whole lot of other maths you can get into if you really want to as well. But you're on your own. I don't understand most of that stuff myself, so I don't claim to. Okay. So that's just a summary of what we got in there. They're a blend of zeros and ones. We're talking in quantum computing, we talk a lot about coherence and interference. So coherence is staying in the state it should do for long enough to do some calculations. And interference is this, whether it's a 0 or 1 or multiplying the amplitudes. And they lead to practical metrics of how good your quantum computer is. Really, they tend to go walkabout. So essentially, they should be a quantum computer. When you put in a certain state, it should be on the surface of the sphere, and it should have a certain phase, a certain angle around the surface of the sphere. And because of quantum mechanics, and because of noise, and because of these things are incredibly delicate, they don't. They drift. So you have to try and put them back into place every now and then, and all that stuff is error correction. So the bit that now actually might make a bit of sense to the room here, hopefully, a bit more sense to the room, I'm hoping, is, that's another picture that doesn't turn out. Excellent. This is going to be good. Okay. So there are cryptographic schemes which are known as information theoretic security. These schemes are not secure because it's hard to decode them. They are, in theory, completely secure. The most famous one of them, if anybody's ever read any kind of spy novels, is the one-time pad. People talk about these one-time pads where you just use a pad, you use it once only. They're random numbers, except random is difficult on a computer. Random's really easy on a quantum computer, by the way. That's it. They are inherently random. One of the first programs I ever wrote on a quantum computer, you can write these things. IBM will give you 10 minutes QPU time on one of their processors for free. You can just go and play. Was actually to run a truly random number between 0 and 15, 4-bit number. Loved it. It took me quite a while to get it going as well, really. So there you go. They can, how that really works. Go look up a one-time pad without the diagram. It's really, I will be here all night, really. I don't know where I'd start, but it's very famous and it is secure. So the holy grail really of computing, of cryptography, is these information theoretic security. But there's always the big problem with one-time pads is you had to distribute these keys. Yeah, and so there were literally people walking around, going in the diplomatic bag, taking these keys around the world to different embassies. Everybody was doing it. And then in the 1960s, somebody came up with public key, which actually two guys working at GCHQ came up with public key cryptography one afternoon, but they couldn't tell anybody because of the Official Secrets Act. And nearly, 15 years later, a couple of guys got, whatever, the Nobel Prize or the Fields Medal or whatever it was for actually coming up with this stuff. And that great thing about that is it's really easy to distribute the keys. The problem with it is that it has always relied on the fact that although it's easy to multiply two numbers together and get a result, if you've got the result, finding the two numbers you multiplied together, extremely difficult. Yeah. And on a classical computer, it would take, for RSA 2048, it would take longer than the known life of the universe. So it was deemed to be secure. In practice, it was always vulnerable to someone, some bright teenager, maths genius, coming up with a better way of factoring numbers. Yeah, and so you've got, some teenager with a Fields Medal around its neck, all the mathematicians in the world thinking, why didn't I think of that? And all the cybersecurity people in the world with their heads in their hands thinking, why couldn't they have been good at football? It's just a nightmare. It always was a nightmare. And Shor kind of made the nightmare a reality. Now, the good thing is we're a long way from having a quantum computer that is powerful enough to break a 2048. You can factor numbers up to a few digits, but nothing close to 2048. So we can relax. Maybe not. We'll see. Yeah. So, this is scaling everything here, isn't it? It's great. Okay, so let's get a little bit more into Shor's algorithm. 1994. It runs exponentially faster than the best known classical factoring methods. It's a hybrid. In other words, part of the algorithm relies on quantum computing and something called a quantum Fourier transform, which is a weird bit of maths that you can apply that runs really efficiently on a quantum computer, and it discovers something called the period, which is a special mathematical function that is related to the keys, to the factors. Yeah, and that's good. And we can't read the bits at the bottom, so I'm not going to try. Okay, so this is it, where you pick a random number, A, that's smaller than n and shares a common factor, shares no common factor with it. Yeah, and so you can pick, there's ways of picking these numbers, but basically, for 15, you pick a number 7, and you then apply this this function to it, which a quantum Fourier transform can to work out really, really quickly to find something called the period. Once you've found the period, you can take half the period, and you very, very quickly can find, using a classical algorithm called greatest common divisor, that will then very, very quickly run that will tell you, which will find you your factors. And the difficulty was always finding this period. They've always known about this. Shor's breakthrough was understanding how a quantum computer could do that. There's two problems, really. Or what's one problem? If there's no fast enough computer out there, we don't have to worry about it. Are there quantum-safe cryptographic methods we could use instead? Yes, there are. But the problem is what is famously known as either HNDL or SNDL, depending on who you want to talk to, which is the store now, decrypt later. Now, would governments admit to doing that? Would bad actors ever admit to doing that? No. I know lots of people who work in those circles who've told me unofficially this is happening. Yeah, storage is cheap. You can store the stuff encrypted in the hope or expectation. Now, it was once the hope, but it's now the expectation that we will build a quantum computer capable of using Shor's algorithm to break the cryptography that is currently used to store most things. So we can change the algorithms to transmit stuff, and that the banks are looking at that very hard at the moment. One of the problems is there's lots of candidates, and of course people want to, the nice thing about public key cryptography is it was very easy to implement. Everyone kind of got behind it, and the infrastructure's out there. Not so much with this, and also the fact that we can encrypt something now that is quantum safe. We think we can. But the stuff that's already been stored, a passing transaction via bank doesn't really make much odds. But actually, the fact that maybe that transaction occurred, and you can prove it occurred, and you can prove the parties that it occurred over, could prove quite embarrassing to people many years after the event. Yes, lots of stuff that could prove quite embarrassing many years after the event. So there's a couple of cute things we can do with quantum safe key distribution. There's a couple of things that we rely on. There's a fundamental tenet, if you like, of quantum mechanics. You can't clone it. You can't clone the state of a bit. You can't copy something exactly. You might sort of think, well, we can't store anything if we can't copy it, but there's ways around that. But the real one is that measurement disturbs the state. Yeah. So if you think of that double slit experiment before, it proved that an electron's a wave. When it hits the detector, it stops being a wave. It collapses into being a thing, a bit, whatever you want to call it. And doing that irreversibly changes it. So if you've got an eavesdropper on the line, they will change what's going on. They will change the state of your message. And there's a couple of different protocols. BB84, the guys who came up with BB84 won the Turing Medal recently. It was announced quite a lot this year. There are variations on it as well. Whoops. So if you're getting into all of this stuff in quantum computing, there are three characters, Alice, Bob and Eve. Now, it's really easy to understand why Eve got her name, because she's the eavesdropper. Why somebody came up with Alice and Bob, I've got no idea. Yeah? But basically, this is all this idea that different ways, there are different approaches of actually being able to send a key safely across a network and absolutely knowing, just using light, things like that, down a fiber optic cable and getting a perfectly secure key. So you can look at that when I actually post up the slides, and you'll see all the pictures as well. Then it's really good. Yeah, and there are other things that we can use as well. The one at the top, one of the things to kind of why I put it in there is SIDH was believed to be secure for quite a long time. And then someone came up with an algorithm that made it not secure, just like that, overnight. And the problem that we've got now really is that in many ways, quantum computers have opened up a new or reinvigorated a branch of mathematics. Essentially, that people are now starting to use some of the ideas behind quantum algorithms to apply those to classical algorithms and showing massive speed-ups. And again, some of the ideas out of classical computing are giving people ideas about how we could do things differently on quantum computers. So, there's really relying on anything that, as I say, is computationally hard is now not very safe. And that's really it. I'll take questions in a minute from anybody. It's coming. It's happening. The quantum computers at the moment are often referred to as NISQ, noisy intermediate scale quantum. And they mean by that is that they don't have too many qubits, and the qubits can wander off track. A lot of work is being done to make these things much more stable. There was quite a thing in the press of Microsoft using Majorana states, and they reckon their next chip, which they should have available by 2029, will be 20 times more stable, at least, than currently. And that makes a big difference. IBM's 2029 computer is looking at 200 qubits and capable of processing 1 million gates. That's their minimum kind of standard, at which point these things get really quite useful. Where are they at the moment? When I first got into computing as a hobby, the AT81 on 8-bit microcomputers, yes, they ran BASIC and you could do a few things on them. If you wanted to make those machines, as I say, really do anything, you had to learn assembler and you had to really understand what was going on. I would say at the moment, that is where quantum computing is. You still got to understand about how all these gates, flip phases and do stuff. There may come a time we just don't have to bother. Yeah. We don't know, but I think they're coming. Cryptography is a threat surface. Most people, my eldest lad is in cyber. He never kind of sits down and thinks, or he didn't until I started talking about this stuff a few months ago to him. And he said, well, we never really think that RSA 2048 is a threat surface. We didn't really think that you can go break it. We've now got another thing to worry about, and you do. Yeah. And the time to be thinking about this is now, I would say. Yeah. Don't wait till someone has stolen your bicycle before you buy a better lock. And you can, depends how much you value your bicycle. And of course, if you buy a better lock, you may never have needed it. It may not happen. But on the other hand, if your bicycle's kind of valuable and there's a better lock out there, I want to think about it. Any questions, guys? Yeah, where do you start? Yeah. Yes.
Thank you. I know 10 times as much about quantum as I did with heavy.
Thank you.
Except I'd heard there were advances in error correcting.
Yes.
I was curious, what's the errors there?
Right. So if only my pictures had turned up, I could explain this a bit better. But if you can imagine a theoretical qubit, if you like, is that the value sits on the surface of this block sphere, of a unit sphere that's a unit of 1. Okay. The errors are that it starts to drift around the surface of the sphere when you think it should be. So you put it into a state where it should be on this point on the sphere, and it just naturally wanders off. Yeah. Now, some of the error correction is if you know the rate at which it's wandering off, every now and again you can give it a kick to get it back to where it was. So that's a lot of the error correction. They're trying to make these. The other thing is almost anything will disturb a quantum state. So they're getting better at building shielding around these things so the errors don't occur. But the main thing about error correction is just getting it back either onto the surface of the sphere. I make the radius 1 again, or kick it back round the sphere to try and get it to the place where you thought you left it. Is the nearest I can come to an explanation. Yeah. There's one, well, I'm just going to put one more slide up there, which is a whole bunch of resources. So I started thinking about, I'll come across this because of an article on BBC back about last October. I signed up for a UCL course, which was, about 120 quid, which wasn't, 2 weeks. And that really kicked things off quite a lot. The National Quantum Computing Centre, you can sign up for a course. They don't have too many licenses. I've got one at the moment. It's actually a Q control course. I don't know how much they cost. They're free through the NQCC. And that's really kicked on my knowledge of these things again. IBM's got lots of stuff. And as I say, for an IBM account, you can get 10 minutes of playing on they've got a thing called IBM Composer where you can play around with these states, or you can play around with these gates. And then you can run it on an actual real computer. They have a simulator in Composer on a real computer. You can do a job, run it on a quantum computer, and it works. It's brilliant. Right. That's it. I probably have about 30 seconds of my minute left.
Near enough, yeah.
Near enough. Yeah, that's a good guess. Anyway, if not, I'm around for the rest of the afternoon, guys. Come and chat about this stuff. Yeah, sorry, yeah.
I was just going to ask, you mentioned there about all answers being in the system simultaneously. You got me thinking back to something that seemed about quantum annealing.
Yeah.
Now that might differ from other approaches, and I'm interested in what those differences are.
No, yeah, they are. We probably are going to get pulled here for a minute, but we're going to have a chat about. I've got some slides on quantum annealing. Basically, it's a way of it's setting up a problem so you've got a certain energy state, and then working towards the correct answer being the lowest energy state, and because the energy states will generally decay to the lowest possible, Quantum annealing machines don't need as much fidelity as quantum gate machines. D-Wave, a company in Canada doing a lot of this, they've got 4,000 to 5,000 qubit, not qubits. People argue, it's like the bloody wars between Oracle and Microsoft and SQL Server years ago. It's just boring, but but we'll have a chat about it outside. If anybody else wants to know about quantum annealing, we'll do that outside. Okay, guys, thank you very much indeed for being such a wonderful audience. And over to the compare.
Yeah, let's have a round of applause for John.